In this lesson, we're going to explore the graphs of polynomial functions. At first, I'm just going to go through some of the theory about what polynomial functions are and how we can distinguish them. Then we're going to do example 1 and 2, which are linear functions. Example 3 are parabolas, so those are quadratic functions. Example 4 you've never seen before, and that's going to be a cubic function. And if you look down in the comments, I'm going to give you the bookmarks for those four different examples. So if you want to jump from one example to the next, or if you want to go back and look at a specific example, you'll be able to do that. And at the very end, we've got a bit of a summary that I've taken from the textbook. Let's get started. So a polynomial function is a function that contains only the operations of multiplication and addition or subtraction with real number coefficients, whole number exponents, and variables. So an example of a polynomial function, you've seen these before. y equals 3x squared minus 2x plus 6 is an example of a polynomial function. We can also write this as f of x, which means that it's a function of x is equal to 3x squared minus 2x plus 6. So these are the exact same thing. So if you want to write yourself a little note here, that when we say y equals, we can also say f of x equals. Those are the same thing. Each part of the function is called a term. So if I want to highlight the terms, I've got 3x squared is one term. Negative 2x is another term, and then the 6 is another term. So those are the three terms in the function, and each term has a coefficient associated with it. So here the coefficient is a 3, here the coefficient is a negative 2, and here the coefficient, well, it's a constant, so there is no variable attached to it. So that's what's meant by constant. And the terms are usually written as descending powers of x, which means if I start with an x squared, then I've got an x in a plain number. Now, does it have to have an x squared and an x? No. This would also be a polynomial function if I had 3x squared plus 6. It doesn't have to have every term in it. It doesn't have to have every descending power, but it always starts with the highest, and then it goes down from there. So here's another example. So if I had f of x is equal to negative 2x squared minus x plus 3. How many terms does that have? Well, it has 3. My coefficients are negative 2 and negative 1. You might say, where's that negative 1? Well, that's right in here. And even though you can't see the 1 there, there is a 1 in there as well. Okay, so that's negative 2 and negative 1 are the coefficients. And the constant term, we already talked about in the first example here, the constant term is the 3 at the end. So 3 is the constant term. Alright, so let's take a look at what other information we can get from our polynomial function. It says here the term containing the highest power of x is called the leading term, and its coefficient is referred to as the leading coefficient. So if I have a function f of x is equal to 4x squared plus 2x subtract 9, the leading coefficient is the 4, and the leading term is 4x squared. Okay? And sometimes we need to know that, okay, what the leading term is or what the leading coefficient is, and we'll take a look at that further. The power of x contained in the leading term is called the degree of the function, or the degree of the polynomial. Now, that also helps us classify our polynomials. So it says polynomials of the first few degrees have special names as listed in the table below. After that, we stop giving them names. It's just a degree 4, degree 5, degree 6. So we're going to name these, okay? So if there is no degree and it's just a constant, then that's exactly what we name it, and you could see the example f of x is equal to 2. If it's got 1 degree, and we don't have to put the 1 in there, but you can see there's an x to the 1, if I make that bigger there, that is our line, right? Y equals mx plus b. Those are linear functions because it's just a degree 1. Right? This is our y equals mx plus b, degree 1, linear functions. Quadratic functions you saw in grade 11, and that's y equals ax squared plus bx plus c is the standard form. So the highest degree is a 2. The leading coefficient has a degree 2. And then a cubic function, x cubed, is the highest degree there. Okay, so the 3 is the highest degree, and so that's our new one. So ax cubed, bx squared, cx plus d. That's our cubic function, and we'll look at all the different characteristics of those because those are new to us. We'll also review some of the other ones. Now it says the constant term is the term at the end of the polynomial with no variable, and I mentioned that earlier, but that's really important to recognize. There's no variable with a constant. Polynomial functions with higher degrees are named after the degree. So this one would have an 8th degree polynomial because the highest degree is 8. That's the biggest exponent in there. There's some characteristics of polynomials that you've seen before and we've talked about before, and I'm going to go through a couple of other ones that might be new to you. Domain and range we've seen before. Domain is the set of all possible x values in a function, where range is all of the possible y values in a function. You need to remember that round brackets mean that those values are not included. Square brackets are for when the values are included, and you can use a combination. So if I had a square bracket and a round bracket, and this was a 2, and this was infinity, that means that the domain, let's say, the lowest value is 2, the highest value is infinity, and because we can't reach infinity, we use that round bracket. Now sometimes you're going to be listing specific points, in which case you would use curly brackets, and then you would list the points that were included. 10, 15, 20, for example. And those are the specific points if we have discrete data. For the most part, we're going to be dealing with continuous data. And sometimes we're going to have to set the domain and range differently according to what's happening in the situation. Setting our window is also very useful to know the domain and range, and that helps set our window as well. For the most part also, for domain and range, we use interval notation. The textbook will be using set notation, so you need to be able to read it, but you don't need to be able to write it. Now, x-intercepts, where the graph crosses the x-axis, this is when y equals 0. Y-intercept is where the graph crosses the y-axis and where x is equal to 0. And I'll show you how to set those and find those using our graphing calculators. So make sure you have those ready for when we get to that point. The end behavior. We're going to be drawing some conclusions and seeing some patterns according to our polynomial functions. So the end behavior is a useful tool to see the shape of the graph from left to right on the coordinate plane. We're going to talk about what happens to the ends of our graph. The turning point is anywhere where the graph of a function changes from increasing to decreasing or decreasing to increasing. And I'll show you an example of that. The easiest example to see is with a quadratic. The turning point is the vertex. Okay? So anytime you have a graph turning around is the turning point. And we'll look at those examples a little bit further as well. We're going to go through 4 different examples, one example for every degree. So example 1 is going to go through degree 0, example 2 for degree 1, and so on. So at this point, if you want to look at each of these separately, I have only one example for example 1, and then I have a couple as we go further on. So if you're good with one and you want to move on, then you're welcome to do that. Or if you want to try one on your own and then see it afterwards, you can do that as well. We're going to go through those characteristics of polynomials for each one of these examples. So let's get started with example 1. Graphing a constant function degree 0. So here you can see there's no variables in my graph, right? F of x is equal to 4. Not 4x, not 4x squared, not 4x plus something. It's just 4. So if you take out your graphing calculator, I can show you how to put this on your calculator. You're going to go into the menu for y equals, and you're going to type in 4 there. So y equals 4. Now to get this to actually graph, you're going to go in and you can hit trace or graph, but you don't know what your window is set as. If we go into window, what that's telling me when we go to window is that my graph is going from -10 to 10 in my x and -10 to 10 in my y. If we just go to a blank page here, I'm going to show you what I mean. So if this is your window, this is what you see on your graph. And currently it's set to go from -10 to 10 in the x and -10 to 10 in the y. So this is your y min, this is your y max, this is your x min, and this is your x max. Okay? So if this window doesn't suit your needs for your graph, you can adjust those numbers so that you can have the maximum space and see what you need to see within your graph. For this first example, this is fine because we're going to be drawing a line, right, a horizontal line at 4, so that's fine. So to get it to graph, I can just hit graph. What I like to do for all of my graphs is hit zoom 6. And zoom 6 is the standard graph, and that always centers my graph at 0, 0 and sets the window from -10 to 10 for both the x and the y. So zoom 6, and there we go. So I've got my horizontal line. Now if you hit trace, it'll tell you in the top corner that y1 is equal to 4. That's the graph that I've just done. And it's also blinking here at my y-intercept. Now it doesn't always do that every single time, but I'll show you how to get to that point. So for right now, let's draw our sketch in at the y-intercept. Go back to our notes page. Okay. So you're going to want to get a straight edge here, right? My y-intercept is at 4 here, so I'm going to put my dot there. And if those numbers weren't labeled on there, you can label it 4. Do not label your intercepts at 0, 4. I don't need the 0 in there. Keep your graphs nice and clean. Okay, so ideally this grid wouldn't be here, and it would just look like this, and you would put a 4 there, and then you would draw your graph, and you would label this x and y. Okay? So at 4, we're going to draw a horizontal line. Notice that I have arrows on the ends of my line to indicate that this graph is going on forever and ever in both directions. It's important that you draw those arrows in. My graph's also labeled x and y. If it's not, then you need to put that in as well. I've labeled my y-intercept, and there are no x-intercepts because this graph doesn't cross the x-axis anywhere. So when we go to fill out this information here, when I write out the domain is from -infinity to infinity. You will always start with your lowest possible value to your highest possible value. Round brackets, because we never get to infinity or -infinity. The range only has one value, and that value is 4. It's not going above or below that, so that is 4. My range. My y-intercept is also 4. X-intercepts, there are none. Not 0. If you put a 0 in this spot, that's telling me that you're going through the axis at x is equal to 0. And we're not doing that, so it's important that you write none. The slope here. What is the slope of a horizontal line? That is 0. End behavior. So what is going on at the ends of this graph? Well, the ends are going from quadrant 2 to quadrant 1. So that's what we're talking about with end behavior. And remember, when we label our quadrants, we label them counterclockwise. So that's how we label our quadrants. And our turning points, there are none. We don't have any increasing and decreasing. That's because we have a slope of 0. So there are none. Let's take a look at an example with a degree 1. In example 2, we're asked to graph two different functions. f of x equals 3x plus 1 and f of x equals negative 2x minus 4. So let's again take out our graphing calculators and put this in and see how to graph it. So go back to the y equals menu, clear out the 4 that we had in there, and instead put in 3x plus 1. Click on zoom 6 to graph, and then trace to give us some important information. Now, we can move our cursor around along here, and that gives us some information, but it doesn't give us the important information that we're looking for. In order to draw a sketch of this graph, I should really know my x-intercept and my y-intercept. In order to find my x-intercept, I click on second trace, which is the calc function, and I'm going to figure out my 0. My x-intercept is also named my 0, so I'm going to click here at 2, and it asks me to go left bound. So if you look where my mouse is up here where the graph crosses the x-axis. That is my x-intercept. So the cursor is blinking to the left of that. So I'm going to hit enter to say, okay, it's to the left. Now it's going to ask me to go to the right. I'm going to move my cursor to the right, anywhere to the right of my x-intercept, and click enter. Now you can see every time I hit enter, I got one of these arrows up here. These arrows are placed on the left and the right of my x-axis. And now it's going to say guess. I'm going to click enter, and the calculator is going to figure out where that x-intercept is. So my x-intercept is at negative 0.3 repeated, and 0. Let's put this on our graph. So if I go here, negative 0.3 and 0 would be about here. Okay, and I'm going to label that as negative 0.33. Just round it to 2 decimal places. What is my y-intercept? We go into another menu, same into second trace, but instead of clicking 1, instead of clicking 2, I'm going to click 1 and put in value. So under there, I could put in any x value I want. So if I want to find the corresponding y value for 5, I would put in 5. If I want to find the corresponding value of negative 3, I'd put in negative 3. But a y-intercept has a corresponding x value of 0. So I'm going to put in 0 here, enter, and it'll give me the y value when x is equal to 0, and it's at positive 1. So right here at positive 1. So now that I have my x-intercept and my y-intercept, I can get my straight edge and draw that graph in there. Let's do that. So again, when you're drawing your line in there using your straight edge, you need to put the arrows at the end to indicate that this graph is going on forever. That's a line, okay, not a line segment, but a full-on line. So our domain would be negative infinity to infinity, because that is going on forever and ever in the x direction, and in fact also in the y direction, using round brackets there. We figured out our y-intercept was at 1, my x-intercept is at negative 0.33 repeated. The slope we can identify right from our graph, because this is in the y equals mx plus b format. If I just put that right above here, you can see your m value is 3. That's your slope. You could also measure that out on your graph by doing the steps, but most easily identified from the equation itself. You could also see your y-intercept from the graph here is at 1. So if you didn't want to use your graphing calculator and you wanted to pick it right out of the equation, you could have done that as well. The end behavior, what quadrant are we starting in? Well, we always read from left to right. So we can see that this graph is going from quadrant 3 to quadrant 1. Now, if the Roman numerals are really bugging you, you could probably put a 3 and a 1 in there instead of the Roman numerals, which is fine. But recognizing that we're going from 3 to 1 is the important part. And again, because there's no turning points here, we would just write none. Okay? This next one says graph f of x is equal to negative 2x minus 4. I'm going to ask you to do that one on your own and then come back and check with my answer. In this example, you can see that because the leading coefficient is negative, my slope is negative, right? I've got a -2 for our slope. If we write that y equals mx plus b, you can see your slope is a -2, so we're going down and to the right instead of up and to the right, which means my end behavior is going from quadrant 2 to quadrant 4 in this case. My y-intercept's at -4, x-intercept's at -2, domain and range go from -infinity to infinity, and there are still no turning points. In example 3, we're going to be graphing a quadratic function. Quadratic functions are degree 2, and their graphs look like parabolas. Now remember that there's different formats for quadratic functions. You can get it in vertex form, in standard form, in factored form. Either way, you're always going to have a degree 2. Sometimes it's a little bit harder to identify, but if you remember the different formats, it'll be a little bit easier to see. Put it in your graphing calculator, it'll always show up for you. So let's look at the first example. F of x is equal to 3 times x plus 1 squared minus 4. A little bit hard to see that that's a quadratic until you remember that this is the vertex form. Okay, let's put it in our graphing calculator and see what it looks like. 3 times x plus 1 squared minus 4. And remembering this is a degree 2, we have that squared. If you FOIL out the x plus 1, you would end up with an x squared term, and that also shows that this is a quadratic. Hit zoom 6, and you can see the picture here. Now remember, for some quadratics, they have 1 0, some of them have no zeros, and in this case, you can see it crosses the x-axis twice, so I actually have 2 x-intercepts. There's also a y-intercept. Now it's really hard to see because everything's kind of squished in that corner, so what I'm going to do is I'm going to change my window so it's a little bit easier to see what's going on in that spot. So I'm going to change my x-min to -5 and my x-max to +5 and see if that helps. Hit trace. And there you can see a little bit better about what's going on. In there you can see that there is an x-intercept and a y-intercept. So if I go second trace value, put in a value of x is 0, I can see that my y-intercept is -1. Put that in here, my y-intercept is -1. And my x-intercepts, I've got 2 of them. So I'm going to go second trace 0. To the first one here, left bound, enter, right bound, enter, enter again, and it's at -2.15. Write that down so I don't forget. -2.15, and there's another one, so second trace 0 again. Left bound, whoops, too far, enter, right bound, enter, enter again, and that would be a positive 0.15. Okay, another important part of a quadratic is the vertex. So how do we get the vertex? Well, I can see that this is a minimum. Remember, a minimum means that it's opening upwards. And when you go and find your vertex, you're going to go in that same menu, second trace or calc, and click on minimum. If you click on maximum by mistake, it's going to give you the wrong value. So click on minimum, and again, we're going to go to the left and to the right of that vertex. Enter, enter, enter again, and my vertex is at -1 and -4. It's -0.999, so I'm going to round that to -1 and -4. Okay, vertex is at -1 and -4. So let's go ahead and graph that. Whenever you graph a quadratic, make sure you label those 3 pieces, the y-intercept, the x-intercept, and the vertex. That's all important information for our graph. Remember, you want a smooth curve when you're drawing your parabola. You don't want a pointy vertex. It's going to be a nice smooth vertex, okay? So nice smooth vertex. Make sure you put arrows at the end, and we can label these points. This is at 0.15, this is at -2.15, and your vertex down here at -1 and -4. Okay, other information that we haven't filled in yet, the domain. Well, remember that with a parabola, these aren't just going up forever, these arrows, they're going out forever too. So our domain here would be from -infinity to infinity. Our range, however, has a limit. It's got a bottom limit, and that bottom limit is at y is -4. And its upper limit, well, it doesn't have one. It's going on to infinity. So it goes from -4 to infinity. Infinity gets a round bracket, but because -4 is included in our graph, I'm putting a square bracket around there. Maximum or minimum? Well, this is a minimum, and the minimum is at -4. Our end behavior, where are those end points? Where are those arrows? Well, they're sitting in quadrant 2, and it goes to quadrant 1. Okay, remember, always reading from left to right. The number of turning points, this graph is our first one that has a turning point, and the turning point is at the vertex, so it's got 1 turning point. All right, try the next graph. The next graph is given in a standard form. We can see it's still a degree 2. You can also see our leading coefficient is negative, and you might want to remind yourself, what does that mean for a parabola? What does that negative do to your graph? Go ahead and try that one on your own, and then check back with my answer. Some important features in this example, that -2, we realize that that makes our graph turn upside down. Not so much the 2, but the negative. The 2 just makes it narrower, right? We've got our axes labeled in x and y, an ordered pair for the vertex, but just the single values for our intercepts. You can see I didn't write those in as ordered pairs to keep it clean. Also, when you write your x-intercepts, students tend to write them out as an ordered pair, and they're not. They're just 2 x-intercepts. Those are your zeros, just listing them so that we know what they are. You can see our quadrant for our end behavior goes from quadrant 3 to quadrant 4, and again, only 1 turning point for a quadratic function. The last thing I'll mention is the range. Again, our domain goes from -infinity to infinity, but our range has no limit for its lowest value. So it goes from -infinity, but it has a maximum value at 3. That's the highest value that this graph can go to. And that's also seen when we do our maximum down here. That relates to the top value in our range. The last example for this lesson is example 4, and we're going to be graphing a cubic function. That's a degree 3, and we haven't seen these before, so it'll be interesting to see what kind of shape they have. Now, you can see the format ax cubed plus bx squared plus cx plus d. And the graph that we're looking at here is x cubed plus x squared minus 2x plus 4. Let's see what this shape gives us. Clear out my other one. X cubed plus x squared minus 2x plus 4. Again, zoom 6 to see what that looks like. So it's kind of this S-shaped graph. Now it's going to be different depending on our coefficients that we have in here, but in general this is the shape. Okay, so as far as everything else goes, finding my domain, my range, x-intercepts, y-intercepts, the exact same thing, but you can see it's like we have a little parabola in there. So in order to find those points on those bumps, we're figuring out our relative maximum and our relative minimum. In our calculator, we're just going to do the same second trace max, second trace min to find out what those vertices are. Alright, let's go ahead and start doing all of this. So if I go second trace value, x equals 0, that'll give me my y-intercept, and that's at 4, so I'll list that. My y-intercept's at 4. Go back. My x-intercept, second trace 0. I'm doing left bound and right bound there. negative 2.46, so I'm going to round that to a 7. Okay, relative max and min. So second trace, I'm going to do the maximum first, that's the bump up. So that's my left bound and my right bound. So that's at negative 1.22 if I'm rounding, and 6.11. So here when it says relative max and min, I don't actually want the whole point, I just want the y value. So that's the 6.11, but I'm going to need that for the graph, so I'm actually going to start graphing this. Remember, the same way we drew a quadratic, how you wanted smooth curves, you didn't want sharp V's at the vertices, you want smooth curves as you're drawing your cubic function as well. Don't forget to label your axes x and y. And we found our relative max, and we found the point, the coordinate point that matches that. That was 1.22, our ordered pair, and 6.11. While I'm here, I can also label my y-intercept of 4, my x-intercept of negative 2.47. So all I'm missing now is my relative min, and to figure out what that lowest value is there. So let's go back into our calculator. Second trace minimum, so that would be 3. And we're going to go left bound here, right bound, guess, hit enter again, and that's at 0.55 and 3.37. So I'm going to here put my y value of 3.37, and on my graph put that ordered pair of 0.55 and 3.37. So there's our cubic function. Mine's exaggerated a little bit, but I kept my scale, okay? My domain for this, you can see that those arrows are going up and out and down and out, so my domain is going to be from negative infinity to infinity. My range is also from negative infinity to infinity. It's going, has no limit, lower limit, and no upper limit. Those are going from negative infinity to infinity as well. The end behavior, reading from left to right, I'm going from quadrant 3 to quadrant 1. And in this case, for our cubic function, we actually have 2 turning points, one at each vertex. Alright, try this again. Try graphing negative 5x cubed minus x squared plus 4x plus 1. And there's a little hint here, this negative does something to your graph, similar to what it does to our quadratic function. So go ahead and figure out all those different characteristics to make sure that you understand how to do that for a cubic function as well. So I hope you tried this on your own first. The toughest part, I think, of this graph was actually putting in your calculator, because if you didn't put it in properly, you wouldn't have actually seen that this graph actually goes above the x-axis, okay? So I actually, whoops, that was supposed to be 0.58. I actually graphed this over here for us, and I changed my window so that it went from, for my x, from negative 3 to 3, and for my y, I went from negative 3, but only up to 0.5, and you can see here that it actually pops over the x-axis just a tiny bit. So I actually have 3 x-intercepts, and this is the other interesting thing about these degree 3s, is you can have more than 2 x-intercepts. We've seen cases for quadratics when we have 2 x-intercepts, but you can have many more x-intercepts for a function that's a degree 3. Okay, so not only do I have 3 x-intercepts, I have a y-intercept, and I have a maximum and minimum. So there's lots going on here. In detail here, the domain goes from negative infinity to infinity. So does the range. My y-intercept is negative 1. I've got my 3 x-intercepts, and I've listed them all and labeled all 3 of them on my graph. The relative max and relative min, And the end behavior goes from quadrant 2 to quadrant 4, and again there's 2 turning points. So sometimes it's not the finding the pieces, but it's what kind of window do I need in order to showcase all of the features of that graph. Let's take a look at the summary on the last page here. Okay, it's a little bit more clear in your notes package, but you can see at the bottom here there's a nice chart summarizing our graphs that we can have for a constant. You can have horizontal lines either above or below the x-axis, your linear functions either with a positive or a negative slope. You can have your quadratic functions that could be maximums or minimums. They can cross the x-axis in 2 places, in 1 place, or in no places. And then our cubic functions, depending on how they're drawn, you can have 2 x-intercepts, you can have 3 x-intercepts, you can have 1 x-intercept, and it depends on how big that relative max and relative min is. The number of turning points can go anywhere from 0 to 2 turning points. It's a really nice summary of that lesson that we've gone through. Thanks for joining me today.